socially responsible.
The laptop is blocking the board for the second time.
Well, last time you all clumped over there, so you had a straight
I
shot at
wasn't
the
over there.
whiteboard.
He was saving your phone.
I was behind your laptop.
Yeah, that's true.
Why'd you sit in the same place?
Yeah.
I don't like change. It scares me.
That's fun. Yeah, there was some, well, anyway, I won't talk about comments on Facebook, but, well, there was one, one where they were like, your audience is online, why are you wearing a mask? I'm like, I think I got a room full of people.
On Facebook, you got fans?
No, sorry, YouTube, not Facebook. Anyway, okay, yeah, people were really happy for me to actually be doing something other than GR and particle physics finally. They were like, oh, thank you so much for doing something new. But they haven't really sat through this and seen how boring it's going to get.
I like
Anyway,
how they act like you have control over the classes you teach every year.
say it again?
Like they act like you are just doing this on a whim and like it's not actual classes that you're teaching on a semi-regular basis.
Oh, really? I never got that impression, but whatever. Okay. So, okay. Are there any questions outstanding from last time? So, who asked me the question about, well, you asked me the question about if I have an even number of intervals. What was it? You said?
If you have an even dimensioned n tuple,
Yes.
and then
And they're real.
yeah.
And they're real. Can you somehow, so were you thinking you would take the real and imaginary parts and,
Yeah, and then you can define it as a vector space over a complex. So you take like a 2n tuple of real, and then you could define it over a field of complex numbers. It seems like at that point you're just defining a complex field or vector over a complex field. But
right. So it's not a real vector field.
so it's okay, good. Yeah.
Okay. And then there was another question that was outstanding. Yes.
On a wheel example with the
Yes, you can do it with complex. Okay, in fact, you can do it with multivariable. You can do it with the function of x, y, and z. And then complex is just it's a function of two variables as well. So yeah, you can do it as well. Okay?
Well,
All
can I
right.
just ask a quick question?
Huh?
Oh, sorry, can I just ask a quick question?
Sure.
So on the tests, is it okay if we just like print out the lecture notes and then use that on the test?
Yeah, that's fine.
On the quizzes? Okay, thanks.
That's fine. Oh yeah, and speaking of your homework, so hopefully you've realized that I've started the homework assignment, and I'm going to update the homework assignment after each lecture, because that's the only way I'll know how far I've gotten. So you're going to have 3 lectures worth of homework for the homework quiz next Thursday, which means you'll get maybe 2 problems next Tuesday, and you'll have from Tuesday to Thursday to get them done. So go ahead and do the four or so problems that you will be assigned from yesterday to today. So just kind of do your homework throughout. Don't just sit and wait and go, I'll do my homework the night before the quiz, because, well, you can. I don't care. Anyway, all right. So to organize our handling of vectors, okay, as you can guess, it is going to be convenient to have a basis. Okay, I mean, this is probably one of the things that you recall from your first working with vectors is, oh, I got to get some orthonormal basis with I hat, j hat, and k hat, and I write the vector in terms of its components along those directions and so forth and so on. Well, wait a minute. How's orthonormal defined? How do we talk about 2 vectors being orthonormal? They're what?
Orthogonal and have a length of 1.
What does orthogonal mean?
It's like a
The dot product is 0.
We don't have dot products yet.
Oh, sorry.
Remember? We have defined a vector space without any mention of a dot or inner product. So one can ask the question, is it possible to conceive of a basis in the vector space without introducing an inner product?
Sometimes.
Turns out the answer is yes, yes.
Could you do it with linear combinations?
Yes. So we don't have an inner product or a dot product of vectors. We don't have a vector times a vector equals a number, but we do have an operation between vectors. That is, we can add them. When you add two vectors, you get another vector back. Okay? So it turns out to define a basis, we can utilize the sum over things. So here we go with our definition. A basis in a vector space V is a set of vectors xi on V that are linearly independent. And moreover, to form a basis, they don't just need to be linearly independent, but they have to span the space. I.e., any vector in the space can be written as a linear combination of the elements of the set xi. It's the definition. Okay, no need to go back and prove this. Notice though, get where you can see, it only relies on vector summation. Okay, linear combinations of vectors are taking vectors and adding them together. Okay, there's no inner product here being mentioned. Now, let's give linear independence a definition. So now I'm going to move away from the idea that it spans the space. Okay? So what I'm going to write is something that seems like it's saying the same thing, but actually I'm just going to write about what it takes for vectors to be linearly independent, not that they have to span a space, and we'll come back to spanning in a minute. So for linear independence, we can say a set of n vectors is linearly independent if and only if the sum from I equals 1 to n of elements of the field over which the vector space is defined times the vectors equals 0 implies that all of those elements of the field are 0. For all I. Okay? Now, where should I mean? What does this mean? Has anybody seen this before? So let's kind of just look at a really simple example to kind of dig into why is it that they're linearly independent if this implies this, okay? So we'll start with an example in R3, okay? And what we'll do is we'll take two vectors, say x3 sorry, x2, and I'll call it x2 and x1. And the angle between these two vectors is arbitrary. It's just not 0 or 180. Okay, it could be 90, it could be 60, it could be 1. Okay? Anything except 0 or 180. Are these two vectors linearly independent?
Yes.
Yeah, they are. Okay, let's see how we can use this criteria to fit it. All right? So first of all, one thing that we know is that we can peel off a piece of the x1 vector which is in the same line or the same direction as the x2, okay? And then we could try and say, okay, well, the x1 piece could be equal to some alpha 2 times the x2 piece. Okay? This piece by itself might not be the same size, but we could scale x2 by some alpha 2, okay? Or we could write this as alpha 2 x2 minus x1 parallel equals 0, okay? Now, obviously, there is another component of the x1 vector which is not collinear with x2, okay? And this can't get canceled by anything from x2, right? So in truth, since this can't be canceled, we have to have alpha 1 be 0, but the alpha 1 is also what's sitting in here, so this is 0, which means alpha 2 x2 is 0, but of course x2 is not 0, so this means that alpha 2 is 0. So as promised, if you have two linearly independent vectors, then the sum over the alphas times the vectors equaling 0 implies that all of the coefficients are 0. Okay? Now, what if we throw in a planar vector, x3? Okay, so now all of these vectors are in the same plane. Even though they are living in R3, they're all living in a plane. Are these three vectors linearly independent? No. Okay. Let's pin it back to this condition. What we can say in this case is that x3 can be written as alpha 1 times x1 plus alpha 2 times x2. And that, of course, means that alpha 1 x1 plus alpha 2 x2 minus x3 equals 0 for non-zero alpha 1, alpha 2, and obviously alpha 3. Okay? Does that make sense? Yes or no? We comfortable with this? Okay. Now we could have thrown in blue means out of the plane. Because if I just do another black arrow in that direction, you might be like, oh, why is it throwing three planar vectors? It's not planar. x3 could have been out of the plane. Would this be a linearly independent set? Yes. And I don't think I need to go through it's basically the same idea as the two arguments that I just made. Okay? All right. So now this is kind of cheating though, because I'm using vectors as arrows and they've got direction. The discussion is way more broadly applicable than that. So consider the following. for P3, does everybody remember what P3 is? Oh, let me pick a card. I got the cards. Zan.
Oh man, so it'd be like polynomials in the third degree?
Yes, exactly. They're polynomials in a variable t up to the third degree, and they could be polynomials in multiple variables or whatever, but we're just going to stick with a single variable. Right. Okay, so let's write down a few vectors in this space. So how about x1t equals t minus t cubed, x2 of t equals 2 plus t squared, x3 of t equals minus 1 plus t, and x4 of t equals minus 2 plus 2t cubed. Are those linearly independent?
No,
How do you know?
obviously, I can make x1 out of x4 and a constant.
You can make which ones?
Looking at x1 and x4, maybe I'm wrong, this looks like I can multiply
Well,
x4 by
Well,
minus 1.
well, this doesn't have, this is a constant and that's a linear.
Oh, my bad.
Yeah. Are these linearly independent?
wouldn't you have to say no because, like, if it's P3 and you have 4 things, then at least one of those has to depend on?
Well, no, P3 is a four-dimensional vector space.
Oh, because it goes from 0.
Yeah, because you have the 0, which has no, yes.
Can't you get x4 from adding x1 and x3?
X4 from adding x1 and
Or
x3.
adding, subtracting x1 from x3 or something like that, and multiplying it by 2?
So let's see, x1 minus x3,
It's not the t.
the t's cancel, so I have minus t cubed plus 1.
And then multiply it by -2.
Oh, damn. Yeah. Guess so.
Ooh, that's pretty good. Okay.
So no, they're not linearly independent?
Well, no, they're not, but my intention for you to figure that out, but that was equally valid. That was perfectly valid. My intention, though, is for you to use this criterion. To ask yourself, is there some linear combination of these 4 vectors that equals 0, but uses coefficients which are not 0? Okay? And it turns out that there is. You can use alpha 1 equals minus 2, alpha 2 equals 0, alpha 3 equals 2, and alpha 4 equals minus 1. So I'm actually glad you introduced the alternative definition of linear independence, and you can therefore prove that these are linearly dependent, but then so too does this condition give us that it's linearly dependent set. Okay?
Is that an alternative definition? Because isn't this definition, even though you're sort of saying different things, like they're both?
Yeah.
All I did was just subtract x4 from both sides of the equation.
Yeah.
Same thing,
Yeah.
so. Or equal.
Okay. All right. So there is a different criterion for linear independence, which actually constitutes a theorem. So let's get away from definitions for a minute and actually consider a theorem. And our theorem says I'll see what I can do about space. The set of non-zero vectors is linearly independent if and only if some xi, and this is a theorem which is essentially what you said, okay? Some xi from I being greater than or equal to 2 up to n is a linear combination of the preceding ones. Okay? So yes, it turns out that the mechanism that you were using is the result of a theorem which can be proven using this condition. So let's do it, okay? Yes, it's an if and only if'er, so we've got to prove it both ways, okay? And I'm not gonna lie, I hate this proof, but I'm gonna do it. I'm gonna do it anyway. So I'm gonna get rid of this. Can y'all, in the Zoom room, can y'all see what I'm writing on the board? Oh my gosh. Oh my God. I'm writing in this narrow column because I feel like that's all anybody can, they can see the whole damn board. Jeez, I gotta expand myself. Golly, why am I being so narrow-minded? Wait a minute, you gotta get that joke.
You should make some marks at the beginning of class to see where you can go and where you can't.
Well, apparently that's the line. I can go to there. And so, yeah, anyway, I don't know what the hell I'm doing, but I would just, yeah. Okay, anyway. All right. What would we do? Now I gotta write all this up high. This could be uncomfortable. Okay, so let's do the if condition. So the if condition is the necessary condition. So, suppose that we start with only one of the vectors. Okay, so we're just going to consider one vector right now. Is that linearly independent? Who says yes? Who says no? So one vector is one vector linearly independent.
It's not zero.
What condition are you using? It's a non-zero vector, yes. A zero vector doesn't play into this story at all. So you have a single non-zero vector. Is that a linearly independent set? Well, I mean, just ask yourself.
Yes.
For the theorem, should there be like a not somewhere in there that like there's some, or like it would not be linearly independent if you can make it out of a combination of previous things?
Oh, sorry. Yeah. Oh, sorry. Yeah. I should have put dependent here. I'm sorry. I should have looked at what I was writing. Yes. Sorry. You're very much right. My apologies. Okay, look. One vector. There's one xi, and it's non-zero. In order for this to be zero, does that mean that alpha I has to be zero? So it's linearly independent. Okay? Does that make sense? All right, so let's do two vectors. Now, if we have two vectors, then obviously this can imply that all of the alpha i's equal 0, in which case this set xi is linearly independent. Okay? Now, at some point in starting with one vector and then going up in the number of vectors in the set, okay? At some point, you will get to a value we'll just call it K, where we transition from a linearly independent set to a linearly dependent set. Okay? So obviously, you know, if I just give you one vector, that's always linearly independent. So to get a linearly dependent set, you have to have more than that. So maybe I draw that, but oh, that's still linearly independent. And I draw this. You know, I draw one out of the plane. That's still linearly independent, but then I go and draw another one in the plane. Oh, damn, our set's now linearly dependent. That's what I'm talking about, this iterative process. Okay? Now here we go. So up to k minus 1, we know that sum over I to k minus 1 of alpha I xi equals 0 implied that all of the alpha i's were 0. Okay? Because at k is when we transition from being linearly independent to linearly dependent. So for all the values of k less than that, we were linearly independent. Here we go. But if I go to k, this implies that some of the alpha i's are not 0. Okay? Because this condition tells us that we have a linearly dependent set. Okay? But this tells us that alpha k itself is not 0. And moreover, the sum to k minus 1 is also non-zero. Okay? Because we have to add in the bit that involves k to this to get this entire condition subject to some of them being non-zero. You can't have just one of them being non-zero. Okay? You follow that? To me, that's the hardest part of this proof to follow. Go ahead.
As a note, when you say not equal to 0, mean not necessarily equal to 0? Because they could still all be 0, right?
Yes, they could.
Okay. Sorry.
Yes, but what we want now is we want to be able to add all through k and get 0 with some of the alpha i's not being 0. And this has got to be at least 2 values. Because you can't have them all be 0 and have one of them be non-zero and somehow have that be equal to 0. So alpha k is non-zero, and then some of the alpha i's up to k minus 1 must now be non-zero. It could just be one, it could be all of them. Okay? But this is non-zero. You follow? Now let me ask you a question. What am I trying to prove?
Trying to prove that you can form the k vector out of the sum of all the other vectors.
Yes, exactly. And now you understand what's going on. So what we can now say is that xk is minus 1 over alpha k times the sum of alpha I xi. All I did was I broke this up. Okay, I broke it up into and then I moved that to the other side, divided by alpha k, which gives me a non-zero answer because this sum has got to be non-zero. Everybody follow? Okay, that's the if. All right, and then we have to do and only if. So are we comfortable with the if part? All right, well, this is recorded, it will be posted, you can go back and look at it, but just kind of getting your head wrapped around these proofs is, I mean, it's what math's all about. Good thing physics isn't about that. Woo! All right. Okay, so the only if is a little bit easier. I'll just get rid of this. Sure we'll need it later, but. So for the only if part, what we can say is, so with the only if part, you want to start with the statement that this is a linear combination of the other vectors. Okay? So we're starting with this result that it's a linear combination of the other vectors. And then what we can do is we can set alpha k equals to -1, in which case this gives us the sum of I to k of alpha I xi equals the sum over I k minus 1 alpha I xi minus xk equals 0. Okay, I mean, really and truthfully, that's just rewriting this. And then, if we go ahead and set all of the higher order coefficients to 0, then what we have is that the sum from I to n, where n is the dimension of the space, we have that the sum over all the vectors is 0 with some of the coefficients being non-zero. Okay? So to prove the if, we started with this and then proved the linear combination. The only if is starting with the linear combination and then proving this. Okay? Remember? Child of two humans is a human. I'll prove that wrong a little later in the course. No, I'm kidding. Okay. I'm kidding. Okay. Any questions about this?
How well do we need to know it?
How well do you need to know it? That's a really interesting question. So, that is a really interesting question. So, first of all, much of this, I want you to understand the definition of a vector space and how far you can take the definition of a vector space in terms of proving various theorems regarding its behavior without casting upon it the additional structure of an inner product. So like I said, normally when you think of a vector space, your immediate reaction is, well, I need an orthonormal basis to work with. But you can have vector spaces upon which you do not define an inner product. And then there's a question, well, is there a reasonable basis? What does it mean? You have enough machinery in the definition of a vector space to establish a basis. It's not as convenient as an orthonormal basis, which is, of course, with a value of which we'll see in due time. But I'm trying to lay things out in the order of development of a basic idea, look at its consequences, and then add to it, and then look at more consequences. Because you all come into the room with a very well-established idea of what vectors are. And the truth is what you know about vectors is way more than just vectors. Okay? So let's start out with defining vectors, and then we'll add all the other stuff in, and you'll get to your normal notion of a vector. It's like, you know, people who walk around and talk about cross products of vectors, giving them back vectors, they're so fucked in the head. I mean, did the cross product of two vectors give you a vector? Who says yes?
Yeah.
Who says no? Well, a lot of you aren't voting.
You
What?
made it sound like people were dumb for saying that a cross product gives you another vector, so I'm kind of scared.
Well, but this is what I'm saying. Like, you've carried around the notion. This is just an example. And I'm not upset with you. I mean, you were taught this. People sat in your math class and they were like, if you take the cross product of two vectors, you get a vector. Okay, right. No. Don't take this negatively. I am not in any way saying, your teacher said the right thing and you learned it wrong. Goddamn. No. I mean, there's just so many things that were thrown at you, and understandably so, because there's a certain framework in which you can work with vectors and you never actually question the reality, the truthfulness of things that you're being said. But can anybody tell me why two vectors cross-producted or it's not a vector?
I mean, if you do differential forms, then you realize they're different objects.
You don't even need to do that.
All right.
I can, should I volunteer?
Sure, Ross, do it.
Well, the reason why the cross product of two vectors is not a vector is because the cross product doesn't transform as a vector under reflections.
Exactly. Vectors versus pseudo-vectors. Aha, yes. Vectors get a minus sign when you reflect all the coordinates. Pseudo-vectors don't. The cross product of two vectors is a pseudo-vector because the two vectors that you're crossing both get a minus sign, so the result doesn't. Okay? But that's if you're actually identifying a cross product as anything vector-like. Because what is the cross product of two four-dimensional vectors?
Messy.
It doesn't work like it does in 3 dimensions. So your comfort with vectors is drawn from, first of all, assuming they have inner products, assuming that they're 3-component things, and then this whole cross product story naturally emerges. That shit doesn't work out for general vectors, and that's what we're talking about here. We're not just talking about a 3-dimensional Euclidean space with x, y, and z. Okay? Is that good? All right, good. And please don't ever think I'm coming down on you for what you do or don't know. Actually, I'll come down on you occasionally for what you do know, because I know some of you are more comfortable with this than me. Okay. All right, let's carry on. And now I'm going to expand and use the entire board.
He's free.
Oh. And part of, I guess, part of this layout, which we will diverge from, we won't just be giving definitions and then proving theorems throughout the entirety of this semester, trust me. But it's kind of giving you an idea of what is the starting point that mathematicians use versus the work that they do with that starting material to derive certain results. Okay, and that's the enterprise of mathematicians, not applied mathematicians. Applied mathematicians just want to use mathematical tools to solve problems, but mathematicians themselves, that is what they do. They define sort of the axioms of what they're going to work with, and then they just sit and they derive consequences from those axioms. Okay? All right, so here we go. Okay. So back to spanning. So we talked about how a basis would be a set of linearly independent vectors which span the space. Maybe I had it there. I wish I still had it up there. But anyway, so we now have a good idea of what linearly independent means. Now let's talk about spanning for a moment. So for spanning, just to give you an example, Well, actually, yeah, so. Well, actually, I'll just. I'll just give you a few examples of vectors which span the space. So first of all, in R3, how many vectors am I going to need if I'm going to span the space? 3. Now it's funny because at this point we haven't actually defined the dimensionality of a vector space. But we have a good sense of what it is. And there is a proof later on about proving the dimensionality. We're not going to mess with that, okay? Because I think it's pretty obvious. But in R3, we have a three-dimensional vector space, which means that a basis of vectors which spans the space should have at least 3 elements. Well, actually, no more than 3 elements, okay? So in R3, clearly, here is a set of vectors of n-tuples which span the space. And you might have said, of course, Alex. That's the set which spans, that's the natural set. That's the orthonormal set. Well, we can't talk about normal yet because we don't have an inner product. But so does this. That is also a complete set of linearly independent vectors in R3. Both of these could form a basis of R3. Your reaction is, but these are orthonormal, these are not. Well, we don't have an inner product defined yet, so we wouldn't classify things by orthonormality or not. So really and truthfully, these are both perfectly good bases in R3, all right? In P3, obviously in P3, we could use 1t squared and t cubed. Actually, I don't want to put that in parentheses because it kind of implies something like this. Okay? So, however, does 1t squared and 1 plus t squared plus t cubed. Okay? So I could use these 4 functions as my basis to build up an arbitrary cubic at largest polynomial in T. This is the obvious choice, right? Because you just put a number, a number, a number, a number, and you've got an arbitrary cubic polynomial in T. But you can do the same thing with this. Okay? All right. So the spanning part is pretty easy. Now, here is an interesting example which might or might not be so obvious, or here's an interesting consequence which might or might not be so obvious. And this is something which I think is painfully obvious if you're working with an orthonormal basis, but it's not necessarily so obvious when all you're working with is a linearly independent basis. Okay? In the orthonormal case, you'll be like, of course, that's, you know, but in a linearly independent basis, this is not so obvious. Every vector has a unique representation as a linear combination of a fixed basis. Okay, and this is a theorem. Okay, so what do I mean here? Well, through the proof, it'll become obvious. consider. Suppose there were two. So there's one representation of the vector x, which is a linear combination of the rest of the vectors in this linearly independent spanning set. And a different linear combination. Okay? Then what I can say is that x minus x equals the sum of alpha I xi minus the sum of beta I xi. Which, now remember our rules for working with elements of the field, elements of vectors, these sort of algebraic structures. This just becomes that. Okay? Again, this is one of those things you're like, oh, those are just numbers. Of course, well, no. I mean, these are numbers, these are vectors, but you can do this. Okay? What's that equal to? Say it again.
0.
It's equal to 0. It's x minus x. It's equal to 0. Oh, wait a minute. If xi is a linearly independent basis, or actually, it doesn't even have to be a basis if it's just a linearly independent set. In order for this to be 0, what does that have to be? It's got to be 0. Which tells us, nope, these two things are the same damn thing. Every coefficient is identical. Yeah?
What is the difference between a linearly independent set and a linearly independent basis?
So, in R3, is that a linearly independent set?
Yeah.
Yes. Is it a linearly independent basis?
No, because it doesn't span.
Because it doesn't span the space. Yeah.
Thanks.
Yeah, this result was just based on a linearly independent set. It doesn't have to span the space. Okay? Everybody follow that one? That was a little easier to follow than the previous one, to be honest with you. That's one of the reasons why I did it. Okay. So, okay. Yeah, I think I could do this. Okay. Any questions before we proceed on? Proceed on. Okay, here we go. We are going to talk about the beauty of isomorphisms. Because they are so beautiful, indeed. All right. So now what I'm going to do is I'm going to step back from vectors for a minute, because it's going to turn out that in the end vectors have a very special isomorphic property. And I'm going to go back to something else we talked about, and those are groups. Okay? So I would like to ask, what does it mean for two groups to be isomorphic to each other. So groups. So if I've got two groups and I want to claim that they're isomorphic to each other, and isomorphic is just a, in math land, it's a really highbrow way of saying this. Except this is something which is well defined in certain functional relationships, and what we're talking about is more, this set is the same as this set, but they're not equal, but they share all of the same properties, so why the hell do you even tell the difference? Okay? Yes?
Oh, I was just gonna ask if it was, if they had the same box thing.
So that's something I thought about doing today, but then I was like, no, we won't do it again. But yes, that's exactly, well, it's that, but there's a preceding, and I'll explain the box thing in a second. There's a preceding condition. If I have a group with 6 elements and a group with 2 elements, are they isomorphic? No. The number of elements in each group has to be the same in order for it to even hope of being the same group. Okay? Same number of elements, okay? But just because 2 groups have the same number of elements does not mean that they're the same group, okay? Because there's more structure to a group than just how many elements does it have. The other part of the structure of a group is what? Oh, Seth. Gotta remember these cards are here. So with a group, you have a set of things, and when I say set, the best you can do is count them. But what else do I include in a group?
And we have some rules, they're associative.
Those are rules about this particular thing that is another part of the definition of a group. So a group, you start out by saying, I have a set of elements and something. What is the something that's also part of the group?
Single operation?
Yeah, we have a single way of combining 2 elements. That single way of combining 2 elements is the second, and it's the last definition of the group. Okay? Now, in order for 2 groups to be isomorphic, they have to have the same number of elements, but the results of combining elements has to follow the exact same pattern. So let me give you some examples of isomorphic groups. And these are going to use what's called a multiplication table. And this is just one way of showing the algebraic structure of a finite group. You can't do this with an infinite group. But if I take the set 1 and minus 1 with multiplication as the group product, okay? Or the group, I should call this the group composition, okay? So I can take these 2 numbers, or, you know, take 2 of these and 2 of these, or 1 of each, and I multiply them. Well, let's write down all of the outcomes. So we know that there are 4 possible outcomes. And the way I do that is I draw a little box. I list the elements across the top. I also list the same elements down the side. And then I ask what happens if I multiply 1 times 1. Yeah, I know you guys were scared of this, but it's pretty straightforward. And believe it or not, I have genuinely messed this up. I genuinely messed it up. And I'll show you the case. So 1 times 1? 1 minus 1? Minus 1, 1? Minus 1 minus 1? Beautiful. Okay? Now, I'm going to give you a totally different group that's actually the same because it's isomorphic. You ready? What do you think E and O means? Even and odd numbers. Doesn't matter what number, just even and odd. And then you're adding. So it's a 2-element group, so the number of elements agrees. The composition is totally different. Here we're multiplying, here we're adding. But those are just names. What we really want to know in claiming these are isomorphic is that the structure of this is going to be the same down here. And it turns out, what happens when you add two even numbers? You get even. Add an even and an odd. Odd and an even. Two odds. Everybody see this? This is the one I screwed up. I was teaching particle like 2 or 3 iterations ago. And I decided to do even and odd with multiplication. Man, it took me a few minutes. One more real quickly. The identity. And a rotation by pi with plus. Oh my goodness, that block is getting curvy, filthy. I don't know what is going on in my head. Well, actually, I can kind of guess. Okay. If I take the identity and I do nothing but the identity to it, I get the identity. If I take the identity, you can take that as a rotation by 0 or 2 pi, it doesn't matter. But if I take a rotation by 0 and then do a rotation by pi with it, what do I get? I get a rotation by pi, a rotation by pi with the identity. 2 rotations by pi is the identity. Okay?
It's true with every 2-element complete group.
That is a very interesting question. If I have any 2-element group, is it always going to have this structure?
You have to have the identity.
The answer is yes, and you'll prove it on your homework.
Right?
But it gets better than that. You're going to prove that any 3-element group has the same structure. Yes?
Just the composition between those groups have to be the same,
The composition between the...
like addition across all the groups.
Wait, say it again?
Like addition across all the groups,
Addition.
multiplication, or whatever the operation is.
The operation can be different between isomorphic groups. It's the result of composing 2 elements that you... It doesn't matter what the transformation or what the composition operation is. What you want are the out products. And so obviously, I mean, hopefully it's obvious, but the structure here is the same as the structure here. I mean, the letters are different, the symbols are different, but we have basically the same thing on the diagonal and the same things on the off diagonal. Yes?
What if we did the first example with the composition of plus instead of multiplication?
This one?
Yeah.
Well, is that going to be a group?
It's not closed.
Yeah, I mean, yeah, that won't be a group.
Yeah.
That's why even and odd with plus, I didn't use 2 and 3. I used just evenness and oddness. Okay, yes?
What about even odd with multiplication?
What about even odd with multiplication? What do you think?
This isn't odd.
It doesn't have an identity in it, right? There's no identity in that group.
Okay, so what you're doing has to be a group. These are all groups. Okay? All right. So, okay, yeah. Okay, so one quick argument is that for this to be isomorphic, it has to go both ways. So what I mean by that is I can take rotations in R3 and I can choose a subset of them which behave identically to rotations in R2. Right? I mean, yeah, if I just, instead of being allowed to rotate around any axis, I just go rotate around one axis. This contains R2. all right? But R2 does not contain R3. So these are not isomorphic groups. Okay, they don't have the same number. Well, it's kind of weird, like how many elements are in the rotation group in R3? It's an infinite number. So you can't count them as easily. It turns out there's more than there are at R2, but we won't worry about that counting, okay? All right, now let's ask, okay, this is great. This is all about groups. We love groups. We're going to spend the last part of this semester studying groups, but we're trying to do vectors. The hell has this got to do with vectors? Well, here's a definition. Two vector spaces U and V over the same field. So these could be, for example, the real numbers or the complex numbers, are isomorphic if there is a local, or sorry, if there is a 1-to-1 correspondence between an element of U and an element of V, and vice versa. So that we can say yi equals f of xi such that this function, which maps me from one vector to another, is linear. Right? And this is a definition. Here's the interesting observation of this definition. It seems like in order to prove the isomorphism of two groups, you have to have a map between elements of this group and elements of this group, right? So 1 becomes evens, -1 becomes the odds. And I know, woke you up. And you have to have a map or a similarity or a likeness between these structures, these compositional structures, these multiplication tables. Oh, sorry. However, notice, in this case, subject to this minor condition, all we need is a map from the elements of one vector space to the other vector space. And the reason for this is because the algebraic structures of vector spaces, they don't have the freedom that we have when we're defining groups. They have these well-defined algebraic structures. Go back to the definition of a vector space. Okay, it's built on the definitions of groups in general, but it turns out the only groups in the definition of a vector space are abelian groups. And then it also is defined in terms of fields. So what this essentially is telling us is that we don't have to worry about the algebraic structure matching up because it always matches up for vectors. So literally, as long as you have a map between each element of one vector space to an element of the other vector space, okay, then those two vector spaces are roughly identical. Think about that for a minute. If I have a three-dimensional vector space, it is isomorphic to another three-dimensional vector space. Okay? But it gets better than that. Because this implies, and we won't prove it, you can read the proof in the book, every n-dimensional vector space which I'll just call V sub n, n's just its dimensionality, over a field F is isomorphic to Fn. That's the set of n tuples composed of elements of the field F. Remember n tuples? Okay. So, and by the way, this is a theorem. I'm not going to prove it. Okay? So if every n-dimensional vector space is isomorphic to Fn, then every n-dimensional vector space is isomorphic to every other n-dimensional vector space, because they're both isomorphic to Fn.
What does that mean again?
What does that mean again?
Yeah. What is it? F superscript n referring to?
So Fn is the vector space. So if n is, if I'm talking about F, so yeah, as an example, if F is the reals and n is 3, then you have a set of 3 real numbers.
Oh, thanks.
If F is complex and n is 4, you have a set of 4 complex numbers. Yeah. We good? Okay. So I'm going to try and bang out one more thing, and then that'll leave us in a perfect place to start next Tuesday. Any questions about this before we move on? Let me go ahead and project ahead so that you can understand the importance of this result. I'm about to introduce an idea which is technically abstract. Okay? It's going to be transformations of vector spaces. Here we're talking about linear transformations for a few minutes. But anyway, however, as a result of this, it means that whatever vector space you're working with, even if it's like polynomials of highest degree 3, that vector space is equivalent to this. And what that will mean for us is that any transformation on a vector space can be written as a matrix. I know.
So tensors are matrices.
No, tensors are not matrices. Screw you, I'm going home. Okay, so let me bust out some information about linear transformation. I'm not going to be complete, but I can at least get the idea out there, and you can buttle on it. And we'll continue this on Tuesday. All right. Wow. And in case you're wondering, like, what the hell's missing? Linear transformations is one of the huge parts of the vector story. And in fact, you rarely do much with vectors that doesn't involve linear transformations. So let's talk about linear transformations for a minute. Okay. Now, first of all, if you want to take a vector space and you want to operate on it or transform it or do something like that, you want to be careful because generally you don't want to screw up its structure and turn it into something other than another vector space. Okay? So a linear transformation is defined such that it preserves the structure of a vector space. So a linear transformation or operator, it doesn't matter. We'll use different words throughout the semester, but they mean the same thing. A linear transformation or operator A on a vector space V assigns to every vector x and y contained in the vector space V, vectors ax, ay, which are also contained on V. Okay? So a linear transformation is not taking us from multiplication of 1 minus 1 to even odd with addition. It's keeping us in the same set. We're talking about vectors here, but the groups is the analogy I'm using. Okay? So it's taking every vector in the vector space, transforming it, but the result is just a different vector in the same vector space. Okay? But to maintain the structure, we have a few conditions it has to satisfy. For A and B scalars, AAX plus BY must be equal to AAX plus BAY. Okay? We can define the product of two of these acting on X in terms of A as a map of the result of first applying the B transformation. So remember, if I start with an element of X and I apply the transformation B, I just get back another, possibly a different element of the vector space, and then I can apply the transformation A to that. So that's how this is defined. Does that make sense? Yes, folks, eventually we will identify this as matrix multiplication, but right now we have not got matrices as part of the story. Okay? And then 3, A plus B on X is AX plus BX. Okay? And again, this is one of those things, I write it down, you're like, of course, it's so stupid, that's numbers satisfy that. No. These are not numbers, these are linear transformations. And this is giving a definition to the sum. It's saying the sum of two linear transformations which acts on a vector gives you the same thing if you enact each linear transformation separately on the vectors and then add the results. This is the sum of two operators acting on a vector. This is the sum of two vectors. So these you have to pay attention to what these things are and don't always just look at this and go, oh, those are numbers, that's obviously true. Okay? This is the definition of a linear transformation. So I'm just going to consider some examples and then we'll bug out. So for an example, for Interpals of field elements could be complex or real. Then matrix multiplication M times V, where V is an element of the space, and M is a matrix multiplying it, with square n by n matrices, works. Satisfies all these criteria. You probably would have expected that, okay? Here is a possibly less obvious example. For the set of polynomials up to degree n, the operator dk, defined as the kth derivative with respect to t, is a linear operator. Let's consider that. dk on ax plus by, where x and y are elements of this space, and a and b are just numbers. Okay? Well, we got dk, dtk, ax plus by, and now you use what you know. This is just a function of t. It's polynomial in t. This is a polynomial in t. These are constants. And so you know the derivative passes beyond the constant and hits the polynomial. So this can be written as that. That's satisfying condition 1. Okay? What about this one? ABX, huh? So if we take dk and we take dk prime acting on x, how do we define that? Well, it's got a nice definition. We do dk dxk of what we get if we do dk prime dt. Am I writing? No, I'm writing t's. That's good. dk prime dtk prime on x. But you know what this gives you?
More derivatives.
Okay. So notice you're not multiplying these together. We look at things like this and we say, oh, you just multiply them together. These are not multiplied together. You know, this is take a certain order of derivative. This is take a different order of derivative. And when you combine them, you're taking a higher order of derivative. You're not just multiplying them together. Okay? And then obviously this one is true as well. Okay?
I had two operators like that together.
You say it again?
You took out the x and you had a plus b there, and you did that with the derivatives. What would you even get? How do you add those two operators together?
Here?
Yeah. You don't just put a 2 in front of it. It's just
How do you add? So this is the definition of how we understand this. So if I have dk plus dk prime acting on x, I enact that as dkx plus dk prime x. And this totally makes sense, right?
Yeah. So you're saying that's true because it's true?
Yeah.
Okay.
I mean, this is how we define, I mean, this expression is how we define how we combine two operators. I mean, it's a definition. Okay, now I want to finish really quickly with one more example, and that is, what about Ix?
What is I here?
I is integrate. I mean, this is the derivative. It's a linear transformation. What about integrating? Is that a linear transformation?
Doesn't it break? It goes a dimension up essentially.
Yes. Remember, if you're an element of Pn, the highest power you get in your polynomial is Tn. But if you integrate that, you get a Tn plus 1 polynomial, which is not an element of the original vector space. Remember, linear transformations have to take a vector in the space and give you back another vector in the space. Okay? All right, so we'll end there. And when we come back next time, we'll talk a lot more about linear transformations, discuss their inverses, and eventually, and we'll show that everything is applicable to matrices and matrix multiplication. And then we'll add the inner product to this story to see all the wonderfulness of orthonormality. Thanks for hanging in there, guys.